Hello everyone, thank you for being here at our talk. We're going to present how we approach the optimization of Pixar next-gen production renderer, RenderMan XPU, to take advantage of wide SIMD instruction sets such as Intel AVX-512. I am Max Liani, lead engineer for RenderMan at Pixar.
And I'm Alex Wells, a principal engineer with Intel. We've been working together to refine practical techniques to achieve coherent execution and improve data access to supercharge RenderMan XPU. But before we get started, I need to display these notices and disclaimers for a couple seconds. Alrighty.
RenderMan XPU is Pixar next-gen production renderer. Fundamentally, it is a physically based path tracer renderer. It is used in a variety of ways, from film and visual effects, where the intent is to closely reproduce the digital match of a principal photography on set, and it is used in animation, where a great deal of stylization and artistic freedom is necessary. Bending physics are at the service of storytelling. Some of our customers use it for scientific visualization and other applications. This breadth of different applications can be an endless source of troubles, and sometimes it results in a great increase in complexity of our solutions. A good chunk of this tech is ready for production. In particular, most of what is needed for look development, which is where part of the scene, including props and characters, are created in isolation and made them look what they are supposed to look on screen. Some other parts of the renderer are a work in progress, such as a number of features used by lighting artists to deliver final frames. Our effort in XPU is to create the next production rendering technology that will take over the existing RenderMan RIS architecture. And this clip that I'm about to show is what RenderMan RIS produces today. What does XPU mean? XPU is our abstract term to identify a generic compute device that we can leverage in a heterogeneous compute architecture. Any compatible device, and here including CPUs as a device, are capable to produce a given picture, and multiple devices of different type can cooperate to speed up the process. Our goal is to let you leverage any hardware you might have, either on a laptop, workstation, a render farm, or over the cloud. XPU produces perceptually identical results across CPU and GPU, meaning that the same image produced by different compute devices will deviate mostly by subtle rounding error, but not in any fundamental way that you will be able to spot with the naked eye. This said, XPU is a completely new renderer, and it does not guarantee an exact match against the current implementation of RenderMan, but the results are close enough to be predictive and representative in nature. This means you might develop an asset in RenderMan XPU and render your final frame in RenderMan RAS if you wish, or at least until RenderMan XPU will be fully featured for the type of final frame rendering in your production. Our problem set is not to create the fastest possible render, is to maximize artist productivity. This graph illustrates the productivity of an artist with a given set of tools. On the horizontal axis is the time it takes for some hypothetical rendering technology to produce a final frame, starting from hours down to the millisecond. On the vertical axis, we have some measurement of productivity of an artist working on a creative task with such a technology. Experience suggests that the faster the renderer is, the more an artist can do within a day. Not only, the better art they can in fact produce by interactively seeing the results and refining their work along the way. So it is not surprise that if a render takes hours to complete, there is only so few iterations an artist can do in a day. And the faster a frame renders, the better, but up to some point. When a renderer completes in a second, maximum productivity is pretty much already realized. Moving down to the millisecond will feel better to the artist, but it will not change by much what they can produce in their work. It is diminishing return past some point. So you see that blue line kind of like going up, as things speeds up, productivity increases. Something that is less known is how much effort an artist have to put on some creation or on the creation of the assets themselves in order to efficiently feed a renderer. The faster you expect a render to be, in general sense, with not just with hard surface, but with hair and fur and volume metrics, and not just a subset of super optimized cases. The faster you expect a render to complete, the more time an artist needs to spend in simplifying and defining assets in optimal ways, which often means taking careful steps and compromises. I'm talking about the whole thing: geometry complexity, shading complexity, texturing, etc. How much of it can be standardized and shared among different assets that compose the scene. There is some degree of correlation between those two lines. The faster you want the render to be, the more optimally defined and configured these assets need to be produced. Because XPU do not aim to deliver real-time rendering, we can work on optimizing for peak overall productivity and not just for peak rendering speed. So we aim to cover the spectrum of application from purely offline rendering up to near real-time rendering. And this is fast rendering, still allowing for great feasibility and quick assets turnaround. Here are some examples of assets rendered in XPU. These images are off-model, and they are assets and characters from our most recent movie, Onward, and they are not exactly as they appear in the movie. This is Barley, one of our hero characters in Onward. The asset is delivered for extreme close-up with plenty of minute details. Texture for his jacket are atlases composed of multiple tiles of 16K by 16K texture resolution, for example. Textures are layered to give high level of control to artists and to adjust the look shot by shot to control, for example, level of wear and tear and dirt. If we weren't enough, fabric is covered in curves to render fuzz and catch realistic backlighting. Skin is also covered by tiny hair, while underneath is simulated with state-of-the-art path trace subsurface scattering. Similarly, this is the manticore. The complexity in this character is about fine displacement, hair and fur, as well as path trace subsurface scatter. In order to explain why production rendering is so computationally expensive, I'm going to spend a couple of minutes on some theoretical digression to make sense of it all. The foundation for us is light transport, which is the physical simulation of light that underpins the entire rendering architecture. In real life, photons are emitted by some emissive surface illuminating the scene. Some of these photons hit scene we frame through the camera, and some travel far away. Photons are reflected, absorbed, bouncing around the scene many times. More of them lost in the process, and a tiny fraction eventually hit the camera sensor, creating a picture. What's important in these scattering events that contributes to light transport from its emission point to the camera, those are the important paths. We call these light paths, and the entire high-dimensional space that represents all possible paths in a scene is called path space. Light transport is an optimization problem of how to simulate this light efficiently. The same math can be easily reused to compute a light path in reverse, starting at the camera, which tend to be how most light transport simulation starts. I will not go into detail, but one thing is obvious here. We are going to trace lots and lots of rays to compute a frame. One thing that perhaps is less obvious is how much computation is required after a ray hits a surface in order to generate the next scattering ray that will contribute to the light transport path. At each ray we hit, we need to evaluate the surface property at the hit point, evaluate shading and texturing that describe the surface property at that point in space, evaluate a bidirectional scattering distribution function, or BXDF for short, which will allow us to sample light and produce new rays to extend light path, and more. For example, along each ray we manage to evaluate extinction and scattering due to participate in media, and more. At the mathematical level, our previous rendering architecture, referred as RIS, which is what our customers use today, and the new rendering architecture, XPU, they both perform the same type of calculations. RIS is designed around the principle of lazy evaluation for pretty much everything, in the hope that some percentage of the scene data won't be actually used. The pros include possible to load very large scenes, and render will never compute some of it. The cons includes a less than ideal thread scaling and fewer opportunities for visualization. So it is a very nice architecture on paper, but very hard to optimize in practice, and even harder to evolve to support heterogeneous compute devices. This is where we decide to start on new rendering architecture for XPU. We took what we learned for continuous optimization on RIS and decided to build something new. We adopted a feed-forward waveform style architecture where compute is subdivided in a subsequent kernels launches. A feed-forward data generation where each kernel launch relies on the fact that any previous kernel will have produced the exact minimal set of data that is required. We restructure data movement in a manner that we can abstract coherency of execution and data access, making it ideal for SIMD, SIMT style execution. Luckily, our design assumptions were right, and we now see the results. In a very simplified way, this diagram is how a waveform renderer works, and is simplified for illustrative purposes. There is a sequence of kernel launches from left to right. You could picture this as a sequence of calculation in a scalar program, However, instead of computing a single ray at a time, we move a lot of samples, a lot of rays through these steps. We start at the camera, generating rays, we intersect them, we keep only those that actually did hit something, we interpolate the surface manifolds that describe the differential point in space, we execute shading patterns on those points, we run scattering for subsurface and volumes, we then compute lighting, eventually we scatter a new ray to continue the light path, and we loop back from the beginning. Each of these iterations in this loop describe a ray surface interaction. And as the light propagates through the scene, bouncing many times, so this sequence loops many times. And these are the wavefronts. In order to extract coherency of execution, we introduced a variety of sorting steps, here highlighted in blue, where we sort by compute kernel. So we sort by execution coherence. For example, we do not have just triangles in our scene. We have a variety of geometric primitive types, such as points and curves. Each of them is fundamentally different, and they interpolate their manifold in different ways. Similarly, and more so, it is for shading pattern and BXDFs, which variety is user-defined and can be unbounded in quantity. Sorting is not free, but it tends to pay off by itself. However, as we gain execution coherence, unfortunately we lose at-axis coherence, since every single kernel launch will execute the points in a different order and gathers data per lane according to their sorted index. So we came up with a more clever unified sorting strategy that maximized the balance between execution coherence and data access coherence, while also reducing the cost of sorting. This vastly improved cache coherence for data access, while data loads of entire vector registers are possible, and data can move across pipeline kernels at a higher level of coherence. So how do we program such an architecture? And it starts in identifying suitable programming models. We need to account for the ability and convenience of development within our team. But RenderMan has a plugin architecture that allows our customer to write their own extensions for their own specific production needs. We need to keep the technical bar as low as possible for everyone, not just our customers, but also ourselves. And we realize most of our customers might not have high-performance computing experts on their payroll. We desire to write kernels as a scalar C++ code that everyone is familiar with, without imposing the developer anything more complex than a piece of code working on a single ray head. It's just simpler than our previous RIS architecture. Code works logically. It is better maintainable without an indexing nightmare. It also serves as a reference version in case of any device-specific specialization or optimization that might emerge as necessary. We have data-oriented C++ code that we can then translate to multiple compute devices. And translation of specific device to specific devices can use different tool chains to generate an efficient instruction set for them. Being able to execute the same kernel between CPU and other less accessible devices can greatly improve the debuggability, unit testing, and validation of kernels without having to reinvent the wheel every time. Some toolchains are mature today, others are emerging, and one example is data parallel C++. The optimization effort that we are about to present have been strategized along a path that allowed us to streamline the renderer and organize efficient computation and data movement today, which paved the path to the adoption of more polished and upcoming programming models tomorrow. So with this, I will give the mic to Alex, that will present the technique and the results.
Thank you, Max. First, let's take a look at the kernel toolchain enabling Intel CPUs. The Intel Parallel Studio Xe. This comprehensive suite of development tools makes it simpler to build and modernize with the latest techniques in vectorization, multi-threading, multi-node parallelization, and memory optimization. The Intel C++ compiler can take advantage of the latest Intel CPU features like AVX-512. It has full C++ 14 and OpenMP 4.5 support, which we'll be using to explicitly vectorize the outer loop over the scalar kernel code. It also has Intel threading building blocks for composable thread-level parallelization, Intel vTone Profiler to find performance bottlenecks fast and inspect the results of vectorizing kernels, and Intel Advisor to further enhance efficient vectorization and threading. And as always, we want to be able to debug, and it has a version of GDB for that. We also have a SIMD optimized version of the Open Shading language, which adds batched interface to push 16 samples through a shader network at a time utilizing AVX-512. And there's an ongoing effort in progress to upstream these improvements to the open source community. RenderMan RIS and XPU both can utilize the SIMD version of the Open Shading language. Despite being a batch renderer, RIS was always fighting for batch utilization. Executing 16 data lanes at a time when the lanes are not full can limit speedups. Observations of the RIS performance inform design decisions for XPU's architecture. By incorporating sorting into the pipeline, XPU has a higher opportunity for overall coherency. In particular, during shader execution, we achieve a higher batch utilization, and optimizations made to stages in the rendering pipeline have higher payoffs. In general, we're seeing higher speedups in XPU with Intel AVX-512. All test results we will show were performed on a 2-socket server using Intel Xeon Platinum 8260L processors. We are testing using all the cores of hyperthreading enabled for a total of 96 threads. All tests were performed using internal development builds. We compare the classic RenderMan RIS to the next-gen RenderMan XPU, along with a version of RenderMan XPU with a unified sort strategy specifically built to target Intel AVX-512 and using the SIMD version of the Open Shading language. Let's examine XPU performance using this compute-heavy Gabor statue asset. It utilizes the Open Shading language for shading, in particular an extremely compute-expensive Gabor noise. Because of this, 96% of the time is spent in the Open Shading language, which dwarfs the rest of the rendering pipeline stages. We're comparing speedups to RenderMan RIS, targeting the Intel 64 instruction set, so its performances are going to be our baseline of 1x. Switching to XPU, we observe a modest speedup. Normally it'd be much larger, however, to that dominant cost of the shading system for this workload, its improvements are limited. Now, if we enable the SIMD version of the Open Shading language using AVX-512, we see some great SIMD scaling of 2.6 as the shading system executes in batches of 16 samples. Likewise, for XPU, we see an even better speedup of 3.5x due to XPU's architecture with improved coherency between data lanes executing in kernels and the shading system. We are seeing batch utilization of the shading system upwards of 95%, which really highlights the potential for scaling with AVX-512. Now, let's take that same statue and reduce the dominance of the shading system by switching from Gabor noise to Perlin noise. Perlin noise is much less computationally expensive. There is a speed quality trade-off here, but we now have a more balanced look at how time is spent inside the renderer. Lighting takes the most time at 45%, followed by shading, which is only 36% of the time now, and finally ray tracing, which is 19%. The point is that a lot goes on inside the renderer other than just ray tracing. Now let's see how XPU's new architecture and optimization handle the Perlin noise statue. Once again, we are comparing speedups to RenderMan RIS targeting Intel 64 instruction set, and that'll be our performance baseline of 1. Switching to XPU, we see a great 2.2x speedup thanks to its improved architecture and streamlined data-centric operation. This performance is very promising, but it's not the end of the story. Now, if we target AVX-512 by enabling the SIMD version of the open shading language, we observe only a modest speedup in RenderMan RIS. Despite really good scaling of 2.3x within the shading system itself, it only accounted for 36% of the overall time. Amdahl's law puts an upper bound on the improvement we'll see. Another issue is that the scalar version of OSL's Perlin noise had an intrinsics implementation which already uses 4 SIMD lanes. This reduces our possible speedup when moving up to 16 data lanes. Also, the remaining non-AVX optimized kernels might operate at slower speeds when mixed with AVX kernels. In the end, we clearly come out ahead here and deliver a measurable overall speedup. In spite of RenderMan RES being a batch rendering solution, we have noticed that for a good portion of the shading system, batches were being underutilized. The new architecture in XPU is being designed to solve these problems. So let's try an XPU with AVX-512 and SIMD OSL. Boom, it's supercharged. We see a great 3.8x speedup. It comes from the improved coherency between data lanes, executing in the kernels, the improved batch utilization in SIMD OSL, and more importantly, SIMD optimized kernels for lighting, BXDF generation, and evaluation, as well as interpolating primary variables. All these rendering pipeline kernels operate with AVX-512 and scale up, so not only is the shading system seeing a speed up, so are all the other compute-intensive rendering pipeline stages. XPU unlocks the performance potential of Intel's SIMD version of the open shading language. To drive that point home, let's examine the relative time spent in each of the individual pipeline stages within XPU when rendering the Perlin statue. We see we're spending 40% plus of the time shading with OSL. And moving to Intel AVX-512 with the SIMD version of OSL, we're seeing a solid 3.7x speedup. That 3.7x is pretty close to our theoretical limit of a 4x speedup, moving from 4 wide to 16 wide SIMD for the Perlin noise function. But what about the rest of the pipeline stages? By optimizing the kernels for SIMD, instead of slowing down the rest of the stages, we can get some decent speedups. For example, generating BXDF samples, we see 2x improvement. Now the ray tracing portion hasn't been optimized to take advantage of 16 wide SIMD yet, so trace path raise takes a small slowdown. However, as you can see, that slowdown is easily compensated for by the other stages speedups. As we look at the rest of the stages, many improve. Evaluate light samples sees a 3.4x improvement. Trace shade raise hasn't been optimized yet, so it takes a slowdown, but then Evaluate BXDF samples gets 1.6x. Generate light samples nets a 4.8x speedup. Interpolate prime vars sees a 2.4x speedup, and get camera rays gets 3.2x speedup. And the remaining stages are a mix between unoptimized and optimized, with some speedups and some slowdowns. But overall, the render time achieves a 2x speedup. So, how do we transform a scalar kernel into a SIMD powerhouse? That's what we're going to demonstrate next. So first, use an excellent vectorizing compiler, in this case the Intel C++ compiler version 19 update 5, and then add the necessary compiler flags, such as the instruction set you want to target. in this case AVX-512. Next, we want to instruct the compiler to use all 512 bits of the registers versus just 256, which is the default, and this will allow us to process 16 floating point operations versus only 8. We also want to enable explicit OpenMP directives for outer loop vectorization, and we want to override some internal compiler limits that are intended to prevent excessive memory usage or compile times for very large complex codes. Well, it turns out we have very large complex codes, and so we need to override those limits. Most importantly, we want to turn on compiler-generated optimization reports. Now, these are going to produce some .opt, rpt files right alongside our .o object files. And a major part of optimizing SIMD loops is examining these vectorization reports to discover what problems might exist. The Intel Advisor is a GUI tool that can provide similar information as well. As we have kernels written to operate on a single ray or hit, we can just have a loop that is called for each of them. Maybe inside of a scalar kernel, some inner loops might auto-vectorize, like transforming a vertex by a 4x4 matrix or a dot product, but the number of SIMD lanes for these internal loops is usually only 3 or 4, and not going to take full advantage over 16-wide SIMD. Now, assuming each iteration of the scalar kernel is independent of the other iterations, we can legally execute the outer loop in SIMD. We explicitly tell the compiler it's legal to do so by utilizing the OpenMP directive pragma omp SIMD and place it directly above the loop. Now the compiler will attempt to generate SIMD version of the loop, executing 16 iterations of the scalar kernel at the same time. We also add a Intel C++ compiler directive to claim it's profitable to inline all function calls inside the loop. This can avoid issues when large kernels somewhat arbitrarily exceed internal compiler heuristics and decide not to inline a function call, which can really limit SIMD performance. So what do we get by just enabling a SIMD loop? We're going to examine a BXDF sample kernel. Here, the baseline is a scalar loop executing the scalar kernel. And after translating the kernel into a SIMD loop, boom, we get a 2.1x speedup targeting AVX-512. And I'd like to show you the performance after optimizing the kernel, but we need to actually optimize it first. Let's recount how we optimized this particular BXDF kernel. Because we're generating optimization reports, we can open those and search for the line number where the SIMD loop begins. Next, look to verify that the SIMD loop was vectorized, and we can see the vector length the compiler chose. There'll be a nice breakdown of different types of memory accesses. Unit stride access, masked or unmasked, will yield the best performance. Basically, a single wide load will read an entire cache line into an AVX-512 register. Gathers are efficient, but don't scale well for non-coherent memory accesses. So think of this section as a scorecard for the kernel's memory access pattern. By rearranging data structures from array of structures to structure of arrays where possible, we can shift statistics from gather or strided accesses to unit stride for the win. Finally, there's a vector cost summary, which attempts to compare the scalar cost of a loop with the SIMD version. Please do not consider this a true performance measurement and don't be discouraged by it. Remember, we measured a 2.1x speedup for this kernel. So what is going on here with the cost? Well, it's based on static analysis and doesn't reflect coherent execution. For example, given a series of if-else statements, each with an expensive code block. During scalar execution, only one of those code blocks could possibly execute and contribute to the cost. In SIMD, up to 16 different blocks could execute and contribute to the vector cost. However, when the data is coherent and allows all 16 data lanes to execute the same conditional block and skip the others, the actual cost will be similar to the scalar version. Additionally, the compiler may hoist loop invariant variables outside the loop and create multiple versions of the loop, which are executed with the mask representing the invariant variable equaling a known value. A good example might be a true or false value that is hoisted out of the loop. So multiple versions of loops now exist, and they usually provide really good speedups. However, the effect on the memory access statistics and the vector cost assumes the worst, and that is that all versions of the loop are executed. So that's kind of like a cost multiplier. Again, given some coherency, 90% of the time only one version of that loop will be executing. Another thing to look at are the vectorized math library calls. Intel's vectorized math library usually have very large speedups in SIMD, and this speedup isn't really accounted for in the cost summary. So you may have a loop that appears to slow down, but actually speeds up because of the math library calls that are happening. The point here is to just use the cost summary as a wind vane to see if your code changes are moving it in the right direction, and to use real benchmarking in Intel vTune Profiler to see how vectorizing a loop really speeds things up. Now that we understand that, let's see if we can improve things a bit. Because XPU now sorts its data, we can stop using indirect access of a sorted index and just use a linear index to access data. This allows many gathers and scatters to become strided loads and stores. There used to be 10 scattered stores, which have now transitioned to strided stores, and 5 or 6 gathers have become strided loads. Changing the data layout of some of the context data from array of structures to structures of arrays allows some of the strided loads to then become unit stride loads. Here we see 2 of the strided loads are gone, and we have 2 more unit stride loads in our scorecard, and this reduces the vector cost as well. Next, some good old-fashioned code optimization replaced a huge pile of conditional operations that were being used to shuffle some bits around with some bit twiddling and masking. It took a few tries to get it correct, and you see it didn't affect our memory access pattern at all, but the vector cost drops quite a bit by removing the huge pile of conditional operations. Now, at the top of the report, you'll see a long list of actual memory accesses and the address or variables that are being accessed. And they're usually only listed for suboptimal situations. Now, you can't always get rid of all of these, but some have a more dramatic performance implication than others. We can talk about one of those we ran into. Looking through the list of memory accesses, we see indirect load was emulated. That's a new one. Luckily, how the address is calculated is displayed. Examining it, we see a this pointer at the start of the memory access. Well, in this part of the code, we know that each SIMD data lane is going to have its own this pointer, resulting in all the data reads based on that this pointer to be a gather. Well, that's expected. So why is it emulated? Digging deeper into the structure that's being accessed, we find out that the offset data member is 16-bit unsigned integer. Well, a gather instruction only exists for 32-bit or 64-bit data, and C++ is only generating a read for the size of the data member. It may not be legal to read more than the data member size. So the gather will have to be emulated by emitting 16 individual load instructions with address calculations and then manipulating the loaded values back into a vector register so they're side by side, so they can continue to participate in the rest of the SIMD operations. And this overhead can inhibit scaling quite a bit. We need to do something to mitigate the emulated indirect loads. We could just change the data type to be 32-bit. That would solve the problem. But it will take more space, and that could be a bad thing, assuming it was made 16-bit in the first place to reduce memory usage. It can also change the physical layout of the data structure in memory, which may be an issue if someplace else in the code assumed they could view this data as a 16-bit value. Another approach is to have a 32-bit value with multiple smaller values packed inside of it. In our example, offset and width are combined into a single 32-bit data member. We then need to use access methods to read the 32-bit value, mask off the unneeded bits, and shift the remaining bits down. The point is all this memory accesses will happen as 32 bits, and the masking and shifting will happen in registers, and that's SIMD friendly. The result is the in-memory data layout is the same. There's no increase in memory size taken. So why not use a C++ union? Well, they're often misunderstood and misused. Unions are a common source of aliasing issues, and they're discouraged from being used for type punning anymore. And they can make it harder for a compiler to optimize. Fancier wrappers can be developed, but the idea is the same. Keep the actual read and write to memory as 32-bit or 64-bit values. Gathering data from C++ bit fields can also cause a similar issue, and the mitigation is the same. Use a wrapper to keep the memory access as 32 or 64-bit. Now back to optimizing our BXDF kernel. So to address the emulated loads, we can start just by switching to a 32-bit integer. That way we don't have to update all the code everywhere to use accessors, and we can see what kind of impact it has. So we see we've got one less gather, but if you look at the vector costs, we got a tremendous drop by removing all that overhead and all those emulation of the indirect loads. And that's our biggest improvement in that vector cost so far. We can follow that on with transitioning more of the context data from AOS to SOA, and here we can see we actually transition 2 gathers into 2 unit stride loads, and that further has a good impact on the vector cost. With a combination of all of these changes, we've reduced the vector cost from 420 to 254. That's about a 1.7x reduction in the vector costs. But again, that's not an actual performance measurement, it's just our wind vane. So how does this all actually come out when we measure the performance? We had seen a 2.1x speedup by translating the BXDF kernel to a SIMD loop. And after our optimization efforts, boom, it's 3.6x faster than the scalar loop. The optimization work has paid off handsomely, providing an additional 1.7x speedup. The statue was very compute heavy, with 100% procedural shading, meaning it contained no textures. Let's investigate performance with production quality assets. The Fountain is a production asset, and it's very texture heavy. If we take a closer look, we can see very fine details such as cracks and variances in the stone's surface and minute vegetation growing from it. During scene setup, the Fountain makes use of displacement shaders to shift the vertices positions before we even get to rendering. In this case, about half the overall time is spent in displacement versus the render itself. We have not had an opportunity to optimize the texture subsystem to take advantage of SIMD yet, so currently we expect texture-heavy assets to affect our SIMD scaling. Let's see how it pans out. To start with, we'll look at a breakdown of the time spent between displacement and rendering. We didn't have an easy way to measure this in RenderMan RIS, but we do for XPU. We see roughly half the time is spent in displacement, but with AVX-512, much less time is spent. Despite being texture heavy, we still get a 1.6x speedup of displacement. And we see about 43% of the time is spent rendering, and likewise much less time is spent rendering with AVX-512. Again, despite heavy unoptimized texture usage, we manage a 1.5x improvement in the render time. The remaining time is spent elsewhere is unchanged, so the overall AVX-512 improvement is 1.5x. in the Fountain, and we expect these numbers to further improve as the texture subsystem gets optimized. So let's put these improvements in perspective. We'll compare against RenderMan RIS, so it's our baseline of 1x. Moving to XPU, we see a massive 5.5x speedup versus the previous generation. We really see the improved architecture and lower overhead shine here. Supercharging with Intel AVX-512 brings the speed up to an incredible 8.3x, and we feel there is more fuel left in the tank to go even faster. The kitchen is another texture-heavy scene. It has many different objects and textures. It'll be a good scene to round out our investigation. Let's see how it measures out. As we didn't have an apples-to-apples scene set up for RenderMan RIS comparison, this time we'll use XPU as our baseline of 1x. Moving to Intel AVX-512 with SymDOSL, we see the render time speed up 1.5x. Again, considering the texture subsystem hasn't been optimized yet, this is a really good result. We have more optimizations to make in the new XPU architecture. We can further improve batch utilization, transition to more SIMD-friendly data layouts, and optimize the texture subsystem. Together, this should further magnify the Intel AVX-512 benefits. It's going to be awesome. Moving forward, we'd like to be able to translate the XPU kernels to run on Intel Xe graphics, including upcoming discrete video cards. Let's take a look at the toolchain to enable it. The Intel One API toolkit provides a unified cross-architecture programming model with a suite of compilers, libraries, and tools to enable high productivity and performance across CPU, GPU, and FPGA architectures, while permitting accelerator-specific tuning. Data Parallel C++ is an open standards-based evolution of ISO C++ that incorporates Kronos Sickle and community extensions to simplify data parallel programming. The Intel One API Data Parallel C++ library is a companion to the compiler and provides parallelized C++ algorithms and utilities that are optimized for a variety of hardware. And then we have a familiar set of support tools, Intel vTune Profiler to find performance bottlenecks fast in CPU, GPU, and FPGA systems, Intel Advisor for efficient vectorization, threading, and offloading to accelerators, and GDB for code troubleshooting. We'll also need a version of the open shading language that can produce SPIR-V representations of the user's shader networks to execute on graphics cards. The big takeaway is that we should be able to utilize the same scalar kernels we've been optimizing, as well as the same OSL shader networks for running on Intel Xe graphics. And we are very excited to be part of this innovation. Max and I would like to thank you for your time and attention today. Have a good one, everyone.